Dear colleagues, welcome to a presentation on a two-period model of coastal-urban adaptation. My name is Dmitry Kovalevsky. I am from Climate Service Center Germany, or JERIX, Helmholtz-Zentrum Geesthacht. The presentation is co-authored by Professor Jürgen Scheffran from the University of Hamburg, Germany. The work to be presented has been done within the MOOCs project, of which Professor Scheffran and I are project co-leaders. MOOCs stands for Modeling Urban Dynamics Affected by Climate Change for Coastal Spatial Planning and Management. The work on MOOCs is conducted and financed within the framework of the Helmholtz Institute for Climate Service Science, or HICS, that is a cooperation between JERIX, to which I am affiliated, and the University of Hamburg, to which Professor Scheffran is affiliated. The general objective of the MOOCs project is to support the development of efficient coastal climate services for urban planning and coastal management by applying comprehensive dynamic models adequately reflecting the complexity of urban social-natural systems. More background on the MOOCs project will be provided in two companion presentations of our project team at the Nonlinear Dynamics and Complexity Conference. I will show the references to these two companion presentations at my last slide. And, of course, you are very welcome to visit the MOOCs website at a link provided at the bottom of this slide. To set the stage, some background on coastal cities and climate change. Coastal areas are subject to hazards related to climate change, flooding and erosion resulting from the impacts of waves, tides, storm surges, and sea level rise. And rapid urbanization increases the susceptibility of settlements to coastal hazards. We believe that both urban dynamic trends and climate change effects should be considered in first coastal vulnerability assessments and then urban and coastal spatial planning and management. These planning processes can be efficiently supported by coastal climate services. And particularly, adaptation strategies for coastal settlements can be supported by inter- and transdisciplinary modeling tools. The development of these tools is the goal of MOOCs project. We will now outline the concept of a two-period coastal urban adaptation model. The time in the model is discrete, and there are two periods only, the present and the future. The city generates urban income. The current version of the model doesn't describe economic growth, so, in the absence of climate change, the urban income in the future would be the same as at present, and all urban income at present and in future can be channeled in consumption. However, in the future period, the coastal city will be affected by climate change, leading to sea level rise and climate-related coastal hazards. These will cause climate damage to the city, reducing the urban income. Therefore, consumption in the future will also be reduced if the city doesn't take adaptation measures at present. However, the city planner may choose to take adaptation measures at present. This means that at present, part of urban income can be channeled in adaptation investment at the expense of consumption at present. This adaptation investment in coastal protection can reduce the future climate damage and therefore increase the future consumption. However, the investment decision at present has to be taken under uncertainty, as the quantitative projections of future sea level rise provided by climate science are uncertain. Future climate damage is also assessed with substantial uncertainty. This was a conceptual description of the model. Let us now provide an overview of model equations without going in much technical detail. The first equation is a partitioning of urban income Y0 at present in two channels, investment ID and consumption C0. Here, F is a production function, K0 is the urban capital at present. The second equation describes the reduction of future consumption caused by climate damage. D is climate damage function. K1 is the urban capital in the future. The third equation describes the efficient height of coastal protection, H1D, as a result of investment ID at present. Here, kappa D is the efficiency of investment in coastal protection construction. In the fourth equation, a parameterization of climate damage needs to be specified. We assume that damage depends on the difference between the uncertain exogenous sea level, H1, and the efficient height of coastal protection, H1D, introduced in the previous equation. We also assume that the probability density function for the future sea level H1 is known. We can now rigorously formulate the optimization problem. The city chooses the investment ID to maximize the expected discounted utility of consumption, where the utility capital U is averaged over the uncertain sea level rise. Here, as mentioned, P is the probability density function for the future sea level H1. Capital U is a linear combination of present and future utility of consumption. C0 and C1 is consumption at present and in the future, and beta is a discount factor in between 0 and unity. The smaller the value of beta, the less important the future for the city planner is. We will explore in detail a particular case of the model with the following highly simplifying assumptions. The production function is chosen in the so-called AK form, quite popular in economic models. The utility of consumption is equal to consumption itself. That means that the city in fact maximizes the expected discounted consumption. The PDF for the sea level rise is assumed to be uniform for simplicity. See the blue curve. And the damage function is assumed to be piecewise linear. See the red curve, with a slope inverse to a new model parameter, HS. We omit all the derivations and provide the main result only. It turns out that the optimal investment strategy depends on the value of the following non-dimensional parameter. We define a non-dimensional model parameter B as a ratio of beta AK0 kappa D to HS, where beta is the discount factor, AK0 is the urban income specified by the AK model, kappa D is the efficiency of investment in coastal protection, and HS is the inverse slope of the damage function. So the main result is, if B is less than unity, the city makes no investment in adaptation at all, This is the so-called business as usual strategy. If B is greater than unity, the city makes investment in proactive adaptation. The conditions favorable to the no investment case, B less than unity, are as follows. Low discount factor, that means that the future is, so to say, not so important for the city planner. Low urban income, high construction costs for coastal protection, and slow growth of damages with sea level rise. We come to conclusions. A two-period model of coastal urban adaptation under uncertainty is developed within the expected utility maximization framework. The investment strategy of the city planner depends on the value of a non-dimensional model parameter. Dependent on the parameter value, the city chooses either business as usual strategy with no investment in adaptation at all, or proactive adaptation with investment in coastal protection. In future work, complementary to presented utility maximization approach, we are planning to explore the coastal urban adaptation model within the viable modeling framework. See a companion presentation on the viable modeling framework by Sengupta and co-authors. A reference to this presentation will be provided at my last slide. Many thanks to Elena Ravenskaya, whose two-period global climate economy model, Ravenskaya 2011, inspired the development of our two-period coastal urban adaptation model. Also, many thanks to Shubhankar Sengupta for helpful comments. I would also like to use this opportunity to advertise two other presentations of the MOOC's team at the Nonlinear Dynamics and Complexity Conference. In particular, the first presentation by Sengupta and co-authors is devoted to the viable modeling framework. And thank you very much for your attention.